Hello, my name is Daniil Musatov, and I want to present a joint work with my student Alexander Grishutin about discrete versions of KKM lemma and their PPAD-completeness. So firstly, I want to briefly explain what is this talk about in general. So it's about fixed points. Fixed points is a large mathematical area that also has a lot of applications in economic models. And 30 years ago, this topic was considered by complexity theorists, and since then they studied complexity of many particular search problems, searching for fixed points, and invented some complexity classes. Because, of course, if we want to apply this theory to some practical search for an equilibrium, then we should be able to compute it, not just to prove that it exists. Okay, so many theorems in this area are about continuous functions, and of course the complexity theory deals with discrete objects. This is why the first step is to invent a discrete version of the theorem. And then we could study the complexity of such problem. So in this work, we do both things for the famous KKM lemma, and I want to start with stating this lemma. So what is it about? So this lemma is about coverage simplex by closed sets. So it was proved almost a century ago, and the statement is the following. So suppose we have a simplex, and it is covered by closed sets, and the number of sets is one greater than the dimension of this simplex. And also there are boundary conditions that any face of the simplex must be covered by the sets that have the same indices as the vertices that form this face. Yeah, so formally you can see what is written here. Then there must be a point that is covered by all these sets. So this is the lemma. It has a lot of beautiful applications and a lot of generalizations, but it is a tricky question how to create a discrete version of it. Okay, so this is an illustration for a two-dimensional simplex for a triangle. So you see that all vertices of the triangle are colored in different colors. So every edge is colored into two colors, and there must be a point colored in all colors in the center of the triangle. Okay, but there is a caveat with discretization. The problem is that the usual way is to consider some approximation or probably some values on some grid. And the problem is that it is hard to create a grid on a simplex, especially if it is not a two-dimensional simplex, but a higher dimensional simplex. And it is much more pleasant to deal with a cube or with a hypercube, because the simplest possible grid is just a cubical grid or hypercubical, and it works in any dimension. This is why it would be nice to consider a cubic version of the KKM lemma. So I show here a quadratic version. So here a triangle is transformed to a square, and we can see the vertices of the original triangle. So they are marked by red dots. So you see that the top edge and the right edge form a single edge of a triangle. Here we have a formal statement of the cubic KKM lemma. Topologically it is the same. So what is important here is it is how we formulate the external condition. So we say that if some coordinate is 0, then this face must not be covered by the set with this index. and if some coordinate is 1, then this face must not be covered by the zeroth set. And if we consider low-dimensional faces, then all conditions must be applied simultaneously. Okay, so we will try to find a discrete analog of this lemma. Okay, so in general, we can split a cube into small equal cubelets, and every cover set must be a union of these cubelets. So we can say that every cubelet must be colored into one or more colors. Okay, so but now the main questions. So first of them, what should be the right analog of closedness? Because closedness is an inherently continuous notion, and we should somehow replace it by some discrete condition. So the next question, what do we want to find? So what should always exist? So a point with some conditions, or a probably multicolored cell. Okay, and the last question is what is the complexity of finding this object? So there are several ways to define a discrete analog of KKM. And I want to start from the general framework. So partly I already said about it. Yes, so to be specific, we have an n-1 dimensional hypercube, and it is split into 2 to the k times n-1 small equal cubelets. So the idea is that the coordinate of a cubelet is specified by k bits. So there are 2 to the k cubelets along any edge, and the total number is 2 to the k times n-1. Okay, so each cubelet is colored into one or more colors. So these colors are from 0 to n-1. And also the cubelets on the faces satisfy the same border conditions. Okay, but what to do with the closedness condition? The first idea is just trivially leave it as it is. So we just consider a figure that consists of some closed cubelets. Yes, so this would be just a union of closed cubelets. And then, in this case, we can just apply the original KKM lemma and obtain a point that is colored in all colors. For instance, here, yes, so here every cell is colored into only one colors. And here there is a point colored in all colors. Okay, so this theorem is correct, but there are some drawbacks. So firstly, we found a multicolored point, not a multicolored cubelet. Of course, here there cannot be a multicolored cubelet if every cubelet has only one color. Secondly, the idea of closeness is not fully captured by this, because in fact we didn't discretize it. Yes, so discrete analog of closeness should be some property of colors of the cells, not of the set they represent. In particular, on a plane or in a space, in Euclidean space, in the coverage of a simplex, if one point is a border point of one set, then it must belong to some other set. And here we don't have an analog of this property. And finally, this statement is very simple. And in fact, it is very close to what is called discrete Sperner lemma. Because in fact, so this picture illustrates exactly the Sperner's lemma. Yes, where every cell has just one color. Okay, then it indeed says that there must be a node surrounded by cells of all colors. Okay, so this is why we didn't stop here and proceed further. So now the second version. Okay, so we leave the general framework and the external condition the same and try to define an analog of the closedness property in the following way. So define a border cubelet, not a border cubelet of the whole hypercube, but a border cubelet of some color. So a cubelet is a border one if it is colored in this color and some of its neighbors is not colored in this color. And now we impose the following condition. Any border cubelet of any color must be colored into some other color. Okay, the question, is it enough to obtain a multicolored cell? Unfortunately, no. And here is an example. Yes, so here our internal condition is satisfied. For instance, this cell is a border cell of the yellow color, and it is also colored in red, and so on. But no cell is colored in three colors. Okay, but what can be said here? Bring your attention to the red point. Among its neighbors, there is a cell colored into yellow and red, a cell colored into red and blue, and a cell colored into blue and yellow. And indeed, this is what we want to state. So the true theorem is the following. Okay, so suppose that there is a square. So this theorem is only in dimension 2. So suppose that there is a square table 2 to the k times 2 to the k, and every cell is colored in at least one color, and the upper left corner is red, the lower left corner is yellow, and the lower right corner is blue. And the conditions on the edges are natural, yes, so the bottom row is yellow and blue, the left one is red and yellow, and the top and the right are red and blue. And also any boundary cell of any color must be colored in at least one other color. Then what can be said? So there must exist a grid node such that among its neighbors all color pairs are present. And it means two cases. So one case is when there is a multicolored set. Yes, for instance, among neighbors of this node, yes, so here we have a pair of red and yellow, a pair of red and blue, and a pair of blue and yellow. And the second case is as before. Yes, so there are three distinct bicolored cells, as on the right panel. Okay, I want to present a proof idea because it is a very beautiful topological idea. Okay, so consider the border of one color, for instance, yellow. Yes, so recall that yellow is here in bottom left corner. So the border of this color looks somehow like this. Okay, so according to our condition, every cell of this border must be colored into also red or blue. And also this point must be yellow and red, and that point must be yellow and blue. Something like this. Okay, so then somewhere along the way, the red and yellow cell must be adjacent to yellow and blue cell, like here. And also, since these are border points, then there must be another cell not colored in yellow, like this cell. Okay, so next there are two cases. So one case, so it is not colored in yellow. So the first case is that it is colored in both red and blue. Like here, then we are done. Yes, so we have 3 adjacent B-colored cells. And the second case is that this cell is colored into only one color. Without loss of generality, it is colored into blue, like this. If blue is the only color, then this cell must not be a border cell of the blue. So then all its neighbors must be colored in blue, including that was already colored into red and yellow. And then we are done. So then we have a multicolored cell. This is what we need. Okay, so we proved the nice and beautiful theorem, but still it has some drawbacks. One drawback is that this theorem is specifically two-dimensional. If we somehow naturally extend it even to the 3 dimensions, then it would be just false. The second drawback is that it does not fully capture the notion of closedness. For instance, consider these 2 cells. So the upper of them is colored into red and not yellow, and the lower of them is colored into yellow and not red. And if you and still they are adjacent. So if you think about continuous sets, then it cannot occur with closed sets. So this is why we invented another third version. So where we directly prohibited this event. So we impose another condition. Say that if cells x and y are adjacent, that it cannot be so that x is colored into one color but not another, and y is colored into another but not the first one. It is easier to show that it is equivalent to the following. So if we consider 2 adjacent cells and consider the color set of the first of them and the color set of the second of them, then one of these sets is just a subset of the other set. And with this powerful condition, we were able to prove 2 theorems. So the first of them is specific for 2 dimensions. Yes, so we impose the new internal condition and consider adjacency as having a common edge. Then the statement is that there must be a multicolored cell. So unfortunately, this is wrong in higher dimensions. But what is true in higher dimensions is almost the same. But if we consider adjacency as having at least one common point, even one vertex. So in this case, there must exist a multicolored cell. Okay, so briefly about proof ideas. So in 2 dimensions, we just apply the second theorem and prove that the case of 3 bicolored cells is impossible under this more powerful condition. And for the case of any dimension, we just apply the original KKM lemma and argue why a multicolored point must be strictly inside some cell. So now I want to briefly consider non-regular tie lengths. So why this first theorem is very, very specific. Even in 2 dimensions, if I consider not a square tie length, but a triangular tie length, then the theorem is false. So this is an example. This coloring satisfies the new internal condition, but still there are only bicolored cells and no 3-colored cell. On the other hand, the second theorem in any dimension also holds for any tiling. Okay, so now let us talk about the complexity of the problem. So in complexity theory, the first step is to specify the problem. And the standard second step is to classify a problem into some complexity classes. Okay, so what is the first step? So what is our problem? So we have some coloring and want to find a multicolored cell or 3 bicolored cells in the second version. Okay, so but how should the coloring be determined? If the set of colors of any cell is given explicitly, then there is no computational problem. We can just look through all the cells and find what we need. So the interesting problem is when we have some succinctly represented coloring. For instance, we have a circuit that is polynomial size and specifies the exponential set of colors for some exponential set of cubelets. Okay, so now the problem is that we are given this circuit and we need to find a multicolored cell. Okay, so what is the complexity? So the first idea that usually arises in such problems is the NP class. Yes, probably NP is the most famous class. But usually for the problems in NP, a solution may exist or may not exist. But if it exists, it is easy to check that it is indeed a solution. Okay, so in our framework, it is easy to check. Since we have a polynomial sized circuit, so then we could generate all the colors and check that all of them are present. And also there is a famous class NP complete. So the class of most hard problems in NP. But for our problem, it is irrelevant because here we just prove the theorem that the solution always exists. And for NP, the problem was, does it exist or not? Okay, so there is a specific class called TFNP, stands for total functional NP, where a solution must always exist and also be easy to check. Well, probably, but in fact, no TFNP complete problem is known, so it is unlikely. So what complexity theorists invented for this case were some subclasses of TFNP called PPP, PPA, PPAD, and many others, where a solution exists according to some mathematical principle. Okay, so these classes do have complete problems, and I want to argue why our problem is also complete in one of them, specifically in class PPAD. So PPAD stands for polynomial parity argument, directed version. So in all such classes, there is one basic principal problem. And here this basic problem or the underlying principle is the directed parity. So if we have a directed graph and for one vertex the in degree and the out degree are different, then there must be another vertex where the in degree and the out degree are different. So usually this class is defined through one basic problem called end of a line. So the principle is the same, but it is applied to graphs that consist only of cycles and chains. So where both out degree and in degree of any vertex is at most 1. Okay, so this is an example of the problem end of a line. Yes, we have such graphs. Yes, we have chains and cycles, and we have a given source. So source means a vertex with out degree 1 and in degree 0. And the task is to find another source or any sink. Okay, so in the first glance, this problem has nothing in common with KKM, but in the second class it does. So we considered some ways along the borders. So in the text of our paper, you may find a more concrete argument why it is relevant here. And in fact, it is not a surprise because there are many papers with PPAD and PPAD-complete problems, and many of them are about mathematical economics, game theoretic equilibria, and so on. So this list is, of course, incomplete. So, and we want to expand this list by the KKM lemma. Okay, so what is our theorem? So our theorem that the problem of finding a multicolored cell in the last theorem, or either a multicolored cell or a bicolored cell in the second theorem. So these problems lie in PPAD and are PPAD complete. Okay, so why is it so? So I show it for the second theorem. And the idea is the following. So we employ the well-known problem called discrete Sperner. We mentioned this problem. So here just every cell must have only one color. The border conditions are the same. And the statement is that there must be nodes surrounded by cells of different colors. So how we employ it? So this problem is well known to be PPAD complete, even in 2 dimensions. And I want to present 2 reductions. So the first reduction is from KKM to Sperner. And this reduction shows that KKM is PPAD. And also it is another way just to prove the statement. And the second reduction in that direction from Sperner to KKM shows that it is PPAD complete. Okay, so now briefly pictures for 2 reductions. Okay, so consider a KKM coloring like this. So I demonstrate 2 cases. Yes, so in this case we have 3 adjacent bicolored cells, and in the right case we have a multicolored cell. Okay, so then replace all yellow cells and yellow-red cells and yellow-red-blue cells by orange cells. So it is done separately on the left and on the right. So next we have red cells and red and blue cells, and we replace them by magenta cells. And the remaining are blue cells and blue and yellow cells, and we replace them by green cells. And now we have again a coloring in 3 colors, and now every cell has exactly 1 color. So we can apply Sperner's lemma and obtain a 3-colored point. It is here and there. And in fact, this point is exactly what we need for KKM. So on the left, it corresponds to 3 bicolored cells, and on the right, it corresponds to 1 3-colored cell. Okay, so that's the idea of reduction KKM to Sperner. So the opposite reduction is performed in the following way. Okay, so suppose we have a grid with a Sperner coloring. And now we consider a shifted and smaller grid. So it is 2 times smaller, and the cells of the new grid correspond to cells, edges, and nodes of the old grid. And then each cell is colored into all colors that correspond to their respective cells, edges, and nodes. So what does it mean? If a cell corresponds to an initial cell, that it has the same color. If it corresponds to an edge, then it has two colors, if this edge is a border between two different colors. And if this new cell corresponds to an old node, then it takes colors of all cells adjacent to this old node. Okay, let me show here. Yes, so this is the initial coloring. So then this is the smaller grid. And then just I color every cell in all colors that occur inside it. So I obtain something like this. Then note that here I have a three-colored cell, and it corresponds to a node that was multicolored in Sperner. And in fact, this is the only variant. There could not be three bicolored cells. Why? Because if we consider any node in the new cell, then at least one neighbor must have exactly one color. And it is impossible for three bicolored cells. So then we can apply KKM, say that the case of three bicolored cells is impossible. So then we must obtain a multicolored cell. And we are done. So this must be a solution. Okay, so the complexity theorem is also proven. This is basically all I wanted to present. I also have two questions for future work. So one question is, what about other versions of the KKM lemma? Yes, because there is plenty of them. Is there anything specific? Are they also in PPAD? And the other question is, could we apply these techniques to some mathematical economical question? Yes, because of course, I think you agree that everything is very beautiful in this presentation, but I cannot see direct applications. Okay, so probably this KKM could be reduced to some other problem that corresponds to some economic model. At least I hope so. Okay, so thank you very much. If you have any questions concerning this paper, please write to me by this email. And you can find the full version in the proceedings. Thank you very much.